Hello, everybody. Good morning to the second talk of this morning. This is the second part of a two-part talk I'm giving. Yesterday, we talked about what the whole enterprise of astronomy is all about. And we started by saying it is concerned with finding the farthest objects in the universe, which are often the faintest objects in the universe, and studying them in the finest detail. And to do that, all that in an as accurate fashion as possible. So yesterday, when we talked about this, we said, look, the main tool of an astronomer is a telescope. And when an astronomer uses a telescope, it does two things for the astronomer. It collects more light from the object, and it allows the astronomer to see more details compared to a human eye. Now, we also found that it is the diameter of the telescope which defines how bright an object becomes, and it is the focal length of a telescope which defines what details telescope can see. And we did some very quick demonstration of how the diameter and focal length define these parameters of how much brighter an object becomes, or how conversely how faint an object you can see, and also what details you can see. We also did this a little bit quantitative, the part where how faint can you see in the sky. And we determined that if there's a star and if there is a background, which we call sky here, background is any background, background or foreground light, which is light just not coming from your target, any light coming from the direction of the target, but not from the target. That is what is called sky here, or background here, or foreground. And we found that the total error in your measurement of how bright that object is given by the fact that if you collect n photons from that object to make a measurement, it is inherently uncertain to root n. And this gave us a way of seeing fainter and fainter objects, because if you collect sufficiently large number of photons from the object of interest as well as the sky, you can ultimately see that the noise, which is typically dominated by the noise from the sky, if the sky is very bright compared to the really faint object you want to observe, the noise from the sky dominates the signal to noise ratio calculation. But by collecting large enough photons, you can keep improving the signal to noise ratio. And where the signal was 10 times weaker than the noise, by collecting more light, we made it equal to the noise. And even collecting even more light, we said the signal can be even 10 times larger than the noise. And therefore, you can have a very certain detection or certain measurement of the light from the object you are interested in. So that's where we stopped yesterday. This is just a recap. Now, what we are going to do today, the two things we are planning to do today, depending on the time. The first thing is to understand what are the limitations of how fine an object, how fine details on an object can you measure. Yesterday we talked about, and this was all about how faint can you measure and what accuracy you can achieve. Today we will talk about what is the details, the finest details you can see when you are looking through a telescope into the sky at celestial objects, and what puts limitations to that, and how astronomers overcome those limitations, and how to quantify the errors which are coming from those limitations. That's what the first target. And if you have time, which I suspect we may not have, if you have time, we will also quickly try to look at the detectors of most interest to astronomers, which are called CCDs, charge coupled devices. We will quickly have a look at how charge coupled devices work, and how basic steps of image processing when you get data or image of a part of the sky using a CCD. So I can't promise we will get there today, but let us see how we go. So let us start with the first topic, which is about how well or how fine details we can see in the sky. I showed this slide also yesterday where it illustrated how telescopes are mounted on, this is a telescope tube, and how telescopes are mounted. This is the alt-azimuth mount where the base on which the mount is made is vertical. And this is the equatorial mount where the base is aligned along the direction in which it is parallel to the axis of rotation of the Earth. Now, both these mounts are used to allow the telescope to look at its target as it moves across the sky and keep scanning, keep tracking the movement of the object in the sky, so that the image of the object stays at the same position at the focal plane of the telescope. Now, here is an image of how targets or celestial objects move across the sky. I don't know how many of you know what is the trajectory look like. So I take a star and take a very long exposure with the camera without moving the camera, without allowing the camera to track the object. So the object will appear to move in the camera's field of view and draw a trajectory across the sky. And these trajectories are circular. You can see many stars here. All the stars form circular orbits or circular trajectories in the sky. And the center of all those circles is the point at which the axis of Earth appears to meet the sky. So you take the Earth, take the axis of the Earth around which it is rotating, project that axis into the sky, and some point in the sky that axis meets. And that is very close to the North Pole star. That is very close to the pole star in the north. And that point, which is the north celestial pole, is the center of these circles. So sitting on Earth, taking a long exposure, all objects appear to move in trajectories which are circular about the north celestial pole in the northern hemisphere and south celestial pole in the southern hemisphere. Now, the rate of the movement we know, Earth rotates 360 degrees in 24 hours, which is equivalent to 1 hour in 1 hour, Earth rotates 15 degrees. So projected from here, this angle which it moves in 1 hour will be 15 degrees. In 4 minutes, correspondingly, it will move by 1 degree. In 1 minute, 15 arc minutes. And in 1 second, the sky moves by 15 arc seconds. So that's the rate at which the telescope has to move to track the movement of an object in the sky. Now, this is just an animation video of that, just a very short animation which shows how the trajectories of the object looks like. Again, this star here is the north pole star, and very close to that, about a degree away, is the north celestial pole, where the axis of Earth meets the sky. And all objects in the sky appears to move in circles around that point. Now, if you build a telescope, is an animation which shows how a telescope has to move. It has to move along this base to point at different directions. It has to move along. This is like raising and lowering your head. The tube of the telescope has to move up and down like this to point at different parts of the sky. So this joint motion, at least in these two axes, one is the base movement as well as the altitude movement. This movement combined together will allow a telescope to track the motion of the objects in the sky. Now, you can see that this telescope is a Gemini telescope. This mirror is 8 meters in diameter. So the total moving mass here is several hundreds of tons. So this several hundreds of tons of moving mass has to be moved in such high precision that the sky, when it moves by 15 arc seconds every second of time, you need to keep that object exactly at the same spot or the image plane of the telescope or the focal plane of the telescope. The telescopes are not operating inside a lab environment. It is out there in the open on top of mountains very often. or at least in observatories which are out there in the open. So when they track objects in the sky, they have to they will be disturbed by various effects like the change of gravity, because as the telescope tube moves up and down, the nature of the gravity, how it affects the primary mirror of the telescope, the secondary mirror of the telescope, etc., keep changing. Temperature variations affect, wind variations affect the tracking. In spite of all this real life disturbances, which the mechanism has to face at an observatory location, the telescope has to keep tracking an object in the sky very, very accurately. Now, in addition to the effect of gravity, temperature, wind, etc., which disturbs the alignment or the pointing of the telescope, there are two other effects coming from the atmosphere. The first one is just a simple refraction, because the atmosphere's thickness and the temperature changes as a function of height as light passes through the atmosphere, especially at angles which are away from the normal direction. Light will bend as it passes through the atmosphere. This is well known. And that refraction causes the apparent location of objects in the sky to be different from their actual location. And the tracking of the telescope has to correct for this effect. So that is effect of refraction, and that's well known, well understood, and is relatively easy to correct for. But what I'm going to talk about today mostly is the second effect called seeing, which is another effect of atmosphere. And let me try to explain that in the next slide. What is seeing? If you take empty space out there far away from Earth, if you take a box of 1 centimeter by 1 centimeter by 1 centimeter, that is 1 centimeter cubed, 1 cc of volume in empty space, there is hardly any particle. You have to take 10 cc of empty space to find even one particle. So space is really empty. On the other hand, if you look at Earth's atmosphere, there is more than 10 to the 19 particles in every cc. So if you take 1 cc sized box at a standard temperature and pressure, there is more than 10 to the 19 particles. So compared to empty space, the atmosphere is a very, very, very dense medium. I cannot put enough number of varies there because you can see compared to 10 to the minus 1, this 10 to the 19. So atmosphere is really dense. So the light which has been traveling from this infinitely far away celestial objects have been traveling through by and large empty space for most of its life. But by the time it hits the atmosphere, the last 100 kilometers or so, it has to pass through a very dense atmosphere. Now, what is the effect of this? The atmosphere is not a very homogeneous medium. It is very disturbed by various processes, like natural processes like the solar heat, winds blowing, convection, and mixing of the air, and so on and so forth. All kinds of activities in the atmosphere make the atmosphere inhomogeneous and continuously mix it up and keep changing. So does human activity. Human activity also produces a lot of disturbances in the atmosphere, and thereby atmosphere become inhomogeneous and turbulent. So yesterday we said that the waves which are arriving at Earth, although they started off as spherical surfaces and radial rays, by the time they travel this infinite distance and reach Earth, they appear like plane waves, because these are really spherical surfaces with infinite radius. So these appear like plane waves, and the rays which are perpendicular to this wavefront are parallel. The rays are parallel. So what happens is, when a bunch of such parallel wavefronts pass through the atmosphere, because of the refractive index at each line of sight through the atmosphere is different and is continuously changing, the wavefronts get totally distorted. So they no more remain as plain wavefronts, but they get completely distorted, because by the time the light ray at this point travel through the atmosphere and reach here at this position in the atmosphere, the light ray which is traveling here and passing through the atmosphere would have reached further because of the effective refractive index and effective path length it found along this path. And this relative variation between refractive indices are continuously changing, because the atmosphere is constantly in motion and it is in turbulence. So the next wavefront would have a completely different shape. And the next wavefront which is passing through the atmosphere would have a completely different shape as they fall on the telescope. So the net effect of all this is that if I look at an image of an object at the telescope focal plane, very, very fast exposure. So you take an exposure which actually correspond to roughly one of these wavelengths, one of these wavefronts. Not all of the wavefronts added together, just one of them at a time, very fast exposure. So the Betelgeuse is a very bright star, and for the WHT, William Herschel telescope, is a very large telescope. So you can collect light from that star very fast and take multiple images very fast and combine them into an automation, an animated movie. So that is the movie which is shown here. So instead of the Betelgeuse image becoming a nice round distribution of light at the telescope's focal plane, you can see that it is a bunch of small blobs of light which all form together into a much larger blob of light, and the whole thing is moving around at the telescope's focal plane. So at any instant, the image of a star would look like one of these images which is frozen in time. Now, if I take a long exposure which collects many of these wavefronts and join together that image, you can see that by then this image on the telescope focal plane would have jumped around so much, and overall it will form some kind of Gaussian distribution of light, because there is always more light in the middle, because some part or other of this blob is illuminating the middle. But as you go further and further to one side, the amount of time the blob spends at that part of the image is less and less, so we get lesser light. So over a period of time, this blob would have moved around this field of view and filled in a way that the light distribution forms some kind of a two-dimensional Gaussian light distribution. So an image of a star at the telescope focal plane would be in a long exposure. Long only in the sense that it is longer than the time at which the atmosphere is changing the shape of the wavefront. And that those time scales, if you add many such time scales and get a joint image, it will look like a Gaussian distribution of light. So that is the nutshell. So instead of getting an ideal image at the telescope focal plane, you get a Gaussian distributed light. Now let us try to understand how this works. This is the ground, and I mentioned this again in my previous talk, the various processes which are disturbing the movement of air, the heat from the ground, convection, solar heat, winds, etc., etc. So energy gets injected into the atmosphere at very large scales, not very locally, at large scale, several kilometers across, because sun is not going to heat the atmosphere locally. It is going to heat it across a large area. Now, as soon as a large patch of atmosphere is heated relative to an adjacent patch, those patches would start breaking down into smaller and smaller patches, so that you can see that the atmosphere packets become smaller and smaller. Energy get transmitted to smaller and smaller size structures, which are all moving relative to each other. These are called eddies, atmospheric air current eddies. And finally, at a very small scale, the viscous forces, etc., start dominating, and the blobs stop breaking up. So if I take a typical atmosphere, there will be eddies or physical structures in the atmosphere at all scales. at scale starting from the scale at which the energy is injected into the system over several kilometers across, to with energy or air packets or eddies which are moving around relative to each other at scales which are smaller and smaller, and ultimately at the size of inner scale, what is called the inner scale, which is size over which it cannot break up anymore. So there is structure in the atmosphere at all these scales at any given time. Now, how does this matter? To understand that, let us look at this image. So if I have a mountain like this, and a laminar stable airflow is blowing across the ocean, which is not disturbed at all. If I locate the observatory on this side of the mountain, the air is undisturbed here, largely. It does not hit the mountain, it's undisturbed. And along this line of sight, as the light passes from Jupiter, along this line of sight, there is very little disturbance in the wavefront shape. They can remain relatively plain as they pass through the atmosphere, and we get a really nice, nicely resolved image of Jupiter. But on the other hand, if we sight the observatory on this side of the hill, this wind which is blowing across this mountain has already been disturbed by the mountain, and it will become turbulent. So as as light from Jupiter passes through this atmosphere, it gets really disturbed, and the distortions induced would wipe away the resolution, and the Jupiter image would look like this. So it is very important to identify the correct location of an astronomical observatory, and you should locate it in a place where the airflow is as undisturbed, as laminar as possible. The moment the airflow becomes disturbed, it disturbs the image quality, and that way you will not be able to resolve fine details of structures on celestial objects which you are looking at. So let us try to quantify this a little bit more. If I have a circular aperture like this, through which I pass a laser beam, and I put a screen very far away, the illumination pattern on the screen would look like this. This is called an airy disk pattern, and many of you have already studied about this. This is just the diffraction pattern of a circular aperture illuminated by a coherent beam of light. So if the telescope was in a place where there was no atmosphere, let's just say it is located in space. So as light passes through the telescope, the primary mirror of the telescope is equivalent to this circular aperture, and the image formed at the focal plane of the telescope would look like an airy disk. So if I have a point source infinitely far away, the beam of light, which are plane wavefronts, which are a coherent beam of light, as they passes through the circular aperture, which is the primary mirror of the telescope, and converges at the focal plane, the image of a star would look like this. If you analyze the distribution of light here in an ideal situation, about 83% of the total light would be in the central disk, and then the remaining light would be distributed along these rings around the central disk. So this is the ideal image formed by any circular aperture like a telescope, primary mirror, illuminated by a plane parallel beam of light, a coherent beam of light. This is true only in the case if there is no atmosphere. But once there is atmosphere, the beam of light does no more remain plane parallel and coherent. Now, what is the angular size of this? This is given by Rayleigh criterion. So if I take a cut along this direction, a horizontal cut along this direction, the distribution of light would look like this. So you follow the cursor here, it goes like this, and distribution of light looks like this. Now, if I put a second star right next to it, its light also would distribute like that. Now, if these two stars are well separated, you will see them as two stars. But if the two stars are not well separated, their light distribution would join together, and in the telescope focal plane, you will see a single blob of light. So the criteria by which you say that a star, two stars or two objects in the sky or 2 point sources in the sky are well resolved is given by the Rayleigh criteria, where if lambda is the wavelength of observation and d is the diameter of the telescope, 1.22 lambda by d is the angular separation at which you take this point and this point. So that angular separation as projected in the sky should be 1.22 lambda by d to say that that object is well resolved. Now, if I take a 10-meter telescope, the largest existing telescope on Earth, and observe at a wavelength of half micron, you plug those numbers in, 10 meter for d and lambda is 0.5 micron. The Rayleigh limit is given by 0.01 arc seconds. What it means is that a 10-meter telescope looking at the sky at a wavelength, collecting light from the sky at a wavelength of half micron, should be able to resolve two objects, 2 points in the sky as two separate points if they are separated by a tiny, tiny angle of 0.01 arc second, theoretically. This should be the theoretically achievable diffraction limited resolution of the telescope. And this should be ideally possible. But what happens in the presence of atmosphere? Now, to understand that, let us look at this figure where instead of one circular aperture, we have put many circular apertures. So this is just like a grating, so which has many open parts and many closed parts, illuminated again from this side by lighter wavelength lambda and plane wavefronts. You know, if you put a screen very far away, the pattern of light distribution on the screen would look like this. These multiple maxima and secondary maxima and minima in between, and so on and so forth. This is the interference pattern coming out of a grating illuminated by a coherent beam of light. Now let us see some relation between the structures on this side and structures on this side. There are three linear scales on this image. The smallest linear scale A is the width of the slit. The next largest linear scale or linear structure, size of the linear structure, is one slit opening plus one block, which I marked here as D. So this width, an opening plus a blocking. And the largest scale structure on this system is the total width of this grating. So at least three size scales exist on this structure, where A, D, and W denote the smallest scale, which is the opening of the slit, the next largest, which is the size of the slit plus the block, and W, the width of the whole grating. Now, if I look at the structures here, there will be one-to-one relation. The smallest structure here, which is A, inverse of that, lambda over A, defines the largest structure at the diffraction pattern, at the far field pattern. So this overall envelope, you know from your theory, is that the single slit diffraction diffraction pattern. So that forms the overall envelope for the multiple maxima, interference maxima you get from these multiple slits. So the smallest structure here defines the largest feature of the distribution of light on the far field pattern. Now the next largest structure here defines the distance between the secondary maxima. And the largest physical structure on the grating, which is W, inverse of that will define the width of the individual maxima, which is this width and lambda by W. So there is an inverse relation. The largest structure here defines the smallest features, and the smallest structure here defines the largest features here. There is an inverse relation. So exactly the same thing happens in the atmosphere. You remember I mentioned that atmosphere has eddy structures at all scales, starting from the outer scale at which the energy is injected, to all the way to the inner scale where the viscosity, etc., stop from the eddies from breaking up further. So atmosphere has structure at all scales. So it is like the situation of a diffraction grating. In the case of diffraction grating, the structure is fixed, it is static, and because of that, the pattern you get on the far field is also static. But in the case of atmosphere, it is like a grating which is continuously changing, because the atmosphere transmission, refractive index, temperature, density, all these properties are changing not only for a given location, but from location to location in an uncorrelated way. So what you expect to see in the image is size scales at all scales compared to in relation to the atmosphere. The largest scale in the atmosphere, which is the diameter of the telescope, scales over the diameter of the telescope, defines the finest features in this blob of light, the smallest blobs into which light is breaking up here. The overall size of this image over a long time will be defined by the smallest features of the atmosphere. And I will come to what that smallest feature is in a minute. So in case where the diameter of the telescope is much smaller than the, let us take R0 as it's called Fright parameter, and it kind of captures what is the size of the smallest eddies in the atmosphere. So if the diameter of the telescope is much smaller than the smallest size eddies in the atmosphere, you can see that the angular width of this will be given by lambda over d, and the time scale over which this would change is given by the diameter of the telescope divided by the wind velocity. On the other case, where the diameter of the telescope becomes much larger than the eddy size, the smallest eddy sizes in the atmosphere, theta is now given by lambda by R0, not by lambda by d. So the resolution you can achieve with the telescope ideally should have been given by lambda over d, where the d is the diameter of the telescope. But when the atmosphere limits it, and when the atmosphere eddy sizes are smaller than the diameter of the telescope, the angular resolution you can get is given by lambda by R0, not lambda by d. And the rate at which these patterns change is given by R0 by wind velocity rather than d by wind velocity. So what I'm trying to emphasize here is, it's no more the diameter of the telescope which defines how fine features you can see and how quickly those features change as a function of time. It is the atmosphere which defines that. The atmosphere, and also the smallest structure, coherent structure in the atmosphere, denoted by this R0, is what defines how fine features you can see and how quickly those features change from time to time. Now, let me put this in context. So again, going back to a diffraction limited image, which looks like an airy disk, we said that if I observe this target with the 10-meter telescope at a wavelength of half micron, the size of this central spot roughly should be about 0.01 arcsecond. But in an atmosphere, the smallest eddy sizes are typically of the order of 10 centimeters or 20 centimeters. So if I put that number, R0, and calculate the diffraction, the size of the image as obtained by the telescope, it will be, instead of 0.01 arcsecond, it will be 0.5 arcsecond, 50 times larger. So what I mean to say is, while I should have been able to see structures on the using a 10-meter telescope, I should have been able to resolve structures which are 0.01 arcsecond separated, angular separated in the sky, because of the atmosphere-induced distortions of the wavefront. I would be limited to resolving objects at 0.5 arcseconds. Any structure on that object which is finer than 0.5 arcsecond, I will not be able to see. That will be washed out by the atmospheric variations. So here, what I put is here is only 0.1 arcsecond. You can imagine what the entire light, which should have been concentrated on a tight spot of this size, would get distributed in a spot which is 5 times this. I can't fit that in my slide here. This is only 10 times larger than this, and then the ratio is 50. So the whole light gets distributed over an area which is 50 times what it should have been in an ideal diffraction limited telescope just because of the atmosphere. So the resolution you can achieve with a 10-meter class telescope is degraded by a factor of 50 because of the atmosphere under these example conditions. Now let me give you a little bit of equations to tell you what this R0 is. I will not get into the details of it because we don't have time. R0, as I mentioned earlier, is the size of a coherent patch in the atmosphere, the linear size of a coherent patch in the atmosphere, the smallest coherent patch. There are coherent patches at all size scales going up to the outer scale, but the smallest coherent patch, which will define by lambda over R0 the overall size of your image at the telescope focal plane. That is given by this expression, where lambda is the wavelength of observation, z or z is the zenith angle or the angle from the vertical at which the observation is carried out. So if I draw a line to the vertical from where I'm standing and a line towards the object I'm observing, the angle between them from the vertical direction towards the direction in which I'm actually carrying out the observation. That is this angle. Cn squared, and the Cn squared is what is called the structure constant, and it is a function of height in the atmosphere. This structure constant defines or captures the information about the disturbance of the atmosphere due to wind, temperature, density fluctuations, etc. This is called the refractive index structure function. So you integrate the refractive index structure function along the line of sight you are going to observe. In this case, you're corrected by sec z, so vertically. And then take this power, and then you get this R0. So your R0 has a lambda raised to minus 6.5 relation. So as the correct connection between R0 and lambda is lambda raised to minus 6.5. So by choosing the longer wavelength, you can actually get better observations because R0 improves. Similarly, theta 0 is nothing but R0 divided by h. So if I put a patch of R0 size at a certain height in the atmosphere, what is the angular size it subtends? And that is given by theta 0. And that, if you substitute in here, would come out to be this expression. And then the time scale over which the atmosphere coherent structures change, and thereby the image on the telescope focal plane also considerably change. That time scale is given by this, where v here, which is the only additional term, v here is the wind velocity at that height. So if at a certain height, there's a certain wind velocity at which things are being churned around, that translates into a time scale over which the atmosphere itself is changing, and therefore the image on the telescope focal plane is also changing substantially. So these are the three parameters which define how much is the impact of the atmosphere in the image quality you can obtain. Now, I mentioned about Cn squared, or Cn squared was a common factor in the three parameters. Now, Cn squared has to be measured and or modeled. So there are many models and there are many measurements which give Cn squared in terms of the wind velocity, in terms of the height in the atmosphere, etc., etc. So I'm just showing here one example, which is called the HV model. And in that model, what is the Cn squared we get as a function of height into the atmosphere. So once you get this expression by measurements and modeling, you can plug that back into these expressions. This is the only part which is unknown, and you can calculate R0, theta 0, and tau 0. So that's the whole process. And then I've shown here what is a typical HV model. Gives R0 to 5 centimeters, theta 0 to 7 microradians, etc., for typical observing conditions. Now, how do we overcome this limitation? This is a very serious limitation, and astronomers cannot live with this limitation. So how do we overcome this limitation? That is what is illustrated in this example here. So think of a telescope which is sending a beam into its focal plane. So the telescope is up there somewhere here. Above that is atmosphere. Light is coming from infinitely far away and falling on this telescope and transmitting through its into its focal plane. Now imagine you are looking at a star which light from which is indicated by this red wavefront. So that red corresponds to the light from coming from the star. Now if we find another star, so if this light passes through this contraption, let us forget these details for now. It arrives at an imaging system like a camera here and forms an image here. Because this wavefront is distorted like this, you get a distorted image at the focal plane. Now, what is done is called adaptive optics. An adaptive optic system, what it does is, by using a guide star, the light from which is indicated by this green line. So you assume the light from a star very close to your target of observation, which is the light shown as red. So they are both arrive at the telescope, reflect off this mirror. I will come to this mirror in a minute. And as they pass through the mirror, when the mirror surface is flat, you get a disturbed wavefront here. But here is a beam splitter which magically, I can tell you how it can be done, but in some way separates the light from the target of observation, send it this way, and the light from the guide star and reflect it this way. So that is the purpose of this beam splitter. Now here is what is called a wavefront sensor, which measures the instantaneous deformation of the light as it comes here, this deformed light as it comes here. It measures the instantaneous deformation, reconstruct the overall deformed shape, and change the shape of this mirror. It is a deformed mirror by applying the right signals here through a control loop. Change the shape of this mirror so that this diffracted or this distorted light, when the mirror changes its shape, exactly becomes a plane wavefront. So once the plane wavefront is formed, as the plane wavefront passes through this closed loop system, in an instant, when the closed loop system is working, you see this is a plane wavefront. These are spherical wavefronts formed by the mirror, and you get diffraction limited perfect images at the telescope focal plane, at the instrument focal plane. You see this light forms a tight spawn rather than a distorted form. So this is called an adaptive optic system. So what you need for an adaptive optic system is a guide star to measure the instantaneous distortions introduced by the atmosphere. You need a beam splitter to separate the light from the target object from the guide star light. And from the guide star light, you use a wavefront sensor to measure the instantaneous distortion. You calculate what shape should this deformed mirror should take so that these distortions are corrected and the wavefront is made parallel. And you do that in a closed loop continuously, very fast, faster than the rate at which the atmosphere is changing. And if you do that, you can end up getting a fully compensated for the atmosphere distortion images at the telescope, at the instrument focal plane. This is called an adaptive optic system. So here is an illustration of an adaptive optic system in work. I don't know if this movie will work. Yeah, this movie is not working right now, so I will skip the movie. That is unfortunate. But you can see that this beam of distorted light, if the movie was working, would have collapsed into a tiny diffraction limited image. And unfortunately, in this animation, this movie is not working. Anyway, so let me, because of time limitation, let me skip through this. I told you that there is a need for a guide star from which the light has to be separated and used for the measurement of the instantaneous wavefront using a wavefront sensor. Now, it is quite often the situation, most of the time, the situation that if you look at a random part of the sky, any galaxy or any star you want to observe, it may be almost impossible to find a bright enough guide star right next to it. So what you do is you create an artificial guide star in the sky in the direction you want. So you create a laser beam, shoot the laser from the observatory through the atmosphere into the sky, and by various processes. In this case, it is a sodium laser. So this laser interacts with sodium molecules in the atmosphere, sodium ions in the atmosphere, and forms a spot of artificial star. And that star can be, because the laser can be pointed in any direction you want, that the star can be created artificially in the direction of the object you want to study. And using that star, the light coming from that artificial star as it passes through the atmosphere, you measure the atmosphere introduced distortions and then correct for it using the adaptive optics system. So this is what is shown here. I showed you this image of the twin Keck telescope on top of Mauna Kea in Hawaii. So you can see two lasers from each of these telescopes shooting into the sky. You are studying this object in the sky with this telescope, and another object in the sky with this telescope. So you're shooting lasers into the sky, creating artificial guide stars, and using that to compensate for the atmosphere introduced distortion. This is just another image of the same. Yeah. So anyway, I will skip through this because of lack of time. Now I'm just showing here a couple of animations to illustrate what difference does adaptive optics make for astronomers. So here is an image of the center of our galaxy. If you look towards the center of the Milky Way galaxy, if you look at it through a telescope without adaptive optics, you will see that all stars are blurred like this. But once the adaptive optics is turned on, you can see how focused the stars are, and then how. So for example, if you keep an eye on this blob, it nicely separates out into 3 stars here. See? Without adaptive optics, you wouldn't know there are 3 stars. It's just one blob of light. And here is actually 3 stars of 3 different brightness. Yeah. And all that detail is lost. For example, there are many, many stars here. None of that detail is available to you unless you have an adaptive optics system, which allows you to see those fine details. So this is another example of an image of Jupiter with and without adaptive optics. Another example of how to study the surface of, I think, the moon with and without adaptive optics, blurred image versus the nice focused image with adaptive optics. Now, this is the holy grail of astronomy currently. We want to look at planets around other stars. If you want to look at planets around other stars, these planets are extremely close to the stars. So you have to first block the light from the star, and then you have to also achieve very, very high angular resolution, because this distance between the planet and the star is very, very tiny compared to the distance to the star from here. We discussed this yesterday. So in order to resolve these planets which are moving around the stars, you need very, very high angular resolution in addition to blocking the light from the star. And the only way to achieve this is by using what is called extreme adaptive optics. You can see here around this star, there are many planets, 1, 2, 3, maybe 4 planets moving around. And you can, over time, you can see here over time of several years, you map the trajectories of those planets, you study their properties, and then understand, for example, does life exist? Is there any evidence of life on that planet? And so on. So I'm running out of time, so I'll skip through some of these. Okay, maybe I'll just cover this part. There are only 2 slides, so let me cover that. So when you use an adaptive optics system, you have to quantify how well it works. Now, the one way of quantifying it is to say, if you remember, at the center of that airy disk pattern, I said there is about 83% of the total light. So if it's an ideal system with no atmosphere and forming diffraction limited images, you should get about 83% of the light in the center spot. Now, if I have a light distracted by the atmospheric effect, of course, the center area will not be that bright. So the ratio of the central brightness of an atmosphere distorted image the Gaussian distributed light distribution, compared to an ideal distribution of light in an airy disk is called the Strel ratio. So this is a quantification of how good your image quality is. If the Strel ratio is close to 1, it means that you get an ideal image. If as the Strel ratio reduces below 1, you get worse and worse effect of atmosphere. Now, the way to quantify the Strel ratio you can show is equal to e raised to minus sigma phi squared. And what is sigma phi? Sigma phi is the residual RMS error in the wavefront, or delta 2 pi by lambda over delta. Delta is the residual path length error. So you take two path lengths to the atmosphere, or the path length averaged over an aperture. Take the RMS deviation of the path length and square that, the mean square path length deviation in either phase or in path length units. E raised to minus sigma phi squared is the loss in central brightness, or is the Strel ratio. Now, any distortion which is introduced can be always broken down into modes for analysis. For example, you have any wave shape, you can decompose it into its Fourier components. You call them modes. So you can decompose any distortion into its component modes. And in astronomy and for optical analysis, very often you use what are called Wernicke modes. Just like sine wave decomposition, sine cosine decomposition of any arbitrary wave shape, any arbitrary shape, you can decompose the wavefront shape over a two-dimensional aperture, circular aperture, into Wernicke modes. So the residual wavefront variance as successive modes are removed by adaptive optic system. So you have an adaptive optic system which only removes the lowest order modes. Then what is the residual wavelength variance? And that variance put in e raised to minus sigma phi squared will tell you how much the Strel ratio is. So if only the lowest modes are removed, the residual wavefront error is almost 1 times d by r0 raised to 5 by 3. If two lowest modes are removed by your adaptive optic system, you will improve the sigma phi. Your residual error is smaller, and you plug that in here, you have a better Strel ratio. And similarly, you say, okay, as they go and remove more and more modes, and finally, if you remove 2n modes, 2n lowest order modes by your adaptive optic system, you get a residual error corresponding to this, and that residual error, when it plugged in here, will tell you what Strel ratio you can eventually get. And that's a quantification of how good your adaptive optic system is. Now, let me finally tell you this is my last slide, quantify why adaptive optics is so important. And that is quantified by this expression here, where if I denote Strel in terms of the signal to noise ratio for a star of given brightness and a sky of a certain brightness. So I am observing a star which is producing flux F using a telescope of aperture D, and my sky, which is called BG here. I'm sorry, it's not called sky here. It's called background, or sky and background are the same. So the sky which is producing F flux, and if I measure this with a signal to noise ratio SNR here, you can see that the Strel ratio scales like d to the 4. What it means is that if I am observing a target in the sky and I am trying to achieve a certain signal to noise ratio, if I do that with a diffraction limited telescope, where the adaptive optics compensates all the atmospheric effect and you get diffraction limited, you get a Strel which is d to the times 4 compared to an instrument which is atmosphere limited. So it is not just the area of the telescope which improves your signal to noise ratio. It scales like the square of the area. So as you make larger and larger telescopes, imagine you have the largest telescope now is a 10-meter diameter telescope. But you are now trying to make a telescope which is 30 meters in diameter. So the improvement in your performance, if you have a good adaptive optic system, is not 30 over 10, it's not 3, which is 30 over 10, which is the ratio of the diameters. It is not even the ratio of the areas. It's not like 3 squared. It is actually 3 raised to 4, which is 80. So as you make bigger and bigger, it's extremely important that you compensate the effect of the atmosphere and get to diffraction limited performance. Otherwise, the loss in performance is really, really large. And that's something which we cannot accept. So that is why adaptive optics is so important in astronomy, and the only way to get to diffraction limited ideal performance and get the angular resolution as defined only by lambda and d, lambda over d, as theoretically possible. Okay, since we are run out of time, let me stop here for now. I unfortunately do not have any time to cover CCDs today and the image processing. Maybe we can do that some other time. I hope you enjoyed the 2 talks we had, and I will now go and try to answer some questions you have raised, if any. So bear with me for a minute. I will stop sharing. Yes, so the first question was, can you please explain how we obtain stable image of an object by observing such dynamically changing pattern? And again, I explained the adaptive optic system. So you must have got the feedback. And your second question was, for adaptive optic system, what is the required time for the feedback to have a stable image? That's a very good question. I also gave you how to calculate that, the tau 0 in the 3 expressions, r0, theta 0, and tau 0. And if you plug in typical values in that expression, as you see in typical observatory locations, tau 0 will come out to be a millisecond or 2 milliseconds or few milliseconds. So the AO adaptive optic system feedback loop has to close at rates much faster than tau 0, which is of the order of few milliseconds. So close to rate of adaptive optic systems are of order of 1 to 2 or few kilohertz. And that is the rate at which the closed loop has to work to compensate for the atmosphere introduced distortion. The next question is from the same person. You've asked, you are saying to create an artificial star beyond the distortion layer of atmosphere, but what if the artificial source created on the region of distortion in the atmosphere, where the rays are not parallel? So how we will tackle this? This is a very interesting question. This is again related to how much money you have, how much resources you have. So if you have a very powerful laser, you can produce a star which is very high in the atmosphere. So the sodium laser guide star, which I showed in my illustration, was at a height of about 90 kilometers in the atmosphere. That is very, very high. So that is pretty good enough. But if your laser, if you can't buy a very expensive laser, you might have to live with a very comparatively cheaper laser, which means you are probing the effect introduced by the atmosphere only to that height. So your adaptive optic system will work, but it will not work and improve the images to diffraction limit. It may improve the image to a certain extent, but not to the theoretical limit or the diffraction limit you need to achieve. So depending on what kind of laser you have, how much power the laser has, and what kind of complicated adaptive optic system you can use, the amount of correction you can implement is decided. And if you have really powerful lasers and really complicated adaptive optic system, you can get a diffraction limit. But otherwise, you have to live with what you have. So it's a choice you make based on your resources, etc. There's a question about providing some reference books. Unfortunately, I don't have it right now. I will provide some references, maybe through some other channel eventually, but I cannot provide them right now. Again, there's a question about share your slides in the space so that we can accept them. I answered this question yesterday. I will try to do that. The slides are available and it's available on YouTube. It is also recorded. So if you get in contact with the organizers of this summer school, you may be able to obtain copies of this talk. But if you just want the slides, please write to me. We will see how we can share it. Then the last question is, does using sodium emission as a guide star compensate for aberration of stars? I don't know what you mean by aberration. Let me assume that the aberration you are referring to is the aberration introduced by the atmosphere. Aberration is a term used to mean many things, but let me assume this aberration is the one which is introduced by the atmosphere. Yes, the sodium emission as a guide star can be used for compensating for the aberration introduced by the atmosphere into all celestial objects, including stars. And there's a reason why you can do that, because we are interested in path lengths, not the atmosphere introduces the same path length to different wavelengths, and by the deformable mirror you are compensating for the path length, not the phase error. And therefore the wavelength is not important while you're measuring the wavefront distortion, to first order at least, and therefore you can compensate for the starlight distortion, although you are measuring only at one wavelength, which is the sodium wavelength. So I think those are all the questions right now from the chat channel. There might be some questions which have come from the YouTube channel, so let me look at those questions and at least try to answer some of them. The first question there is, what are the advantages and disadvantages of putting a deformable mirror at secondary and at next stages? Excellent question. Yes, there are adaptive optic systems in which the secondary mirror itself is made deformable. Now, there are advantages in this, in the sense that you don't need a lot of optics behind the telescope to compensate for the, you minimize the number of surfaces in the entire system, and at each surface there is some loss of light. So if you minimize the number of surfaces, you improve your light gathering power. So using one of the mirrors of the optics itself as a deformable mirror is an advantage. But the disadvantage is the secondary mirrors are often very large. So if you want to deform such a large mirror at the fast rate at which it needs to be deformed, like kilohertz rates, it becomes very complicated. And the manufacturing of such large deformable secondary mirrors is a very, very challenging problem. So that is the disadvantage. There is a second disadvantage, that if you look at the deformable mirror and project it back through the telescope into the sky, it will form an image of the deformable mirror in the sky. So that is the typical height from which you are correcting. That is a conjugate plane of the deformable mirror in the sky. Now you want that conjugate plane to be as high in the sky as possible so that you can correct for as many layers of the atmosphere. Now in a typical telescope system, if the secondary mirror is used as the deformable mirror and you project the image of the secondary mirror back into the sky, very often it may be not very high in the sky. It may be even below the ground. And because of this, you may be correcting only for the lower atmospheric layers. And that is another limitation of using secondary mirror as a deformable mirror. The next question is, does polarization information get affected when we use adaptive optics, and how AO will help in polarimetric observations? This is a very, very complicated subject because an adaptive optic system often have many mirrors, many optical components in its beam path. You saw the deformable mirror, the beam splitter, the wavefront sensor. They all will have a lot of optics embedded in them. And each of them can affect the polarization state of light. And it is not, the answer to your question is not it's not a unique answer. It actually depends on the details of the system. So the polarization does get affected by the adaptive optic system. And AO, to say that AO will help in polarimetric observation or not will depend a lot on the details of how the AO system is set up, what is the nature of polarization you're trying to measure, how accurately you want to measure, etc. So that answer is not unique. It will depend on the specific details. Now, the last question in the YouTube channel is about how will the increase in the diameter of the telescope improve the image quality despite the presence of atmosphere? I think this question might have been posed before I explained adaptive optics. So the whole idea of adaptive optics is to compensate for the effect of the atmosphere in reducing the image quality. And an adaptive optic system is the solution. And that would have answered this question. So I think that's all the questions I've received so far. I have tried to answer all of them. Then let me close. Let me see. There is one more question from another participant in the chat channel. I will answer just that question and then we'll have to stop. Can statistical techniques like singular value decomposition account for missing adaptive optics? Now, I don't fully understand this question, but let me try to answer this in a way following. In an adaptive optic system, the connection between the geometry of the wavefront sensor and the geometry of the deformable mirror or the correcting surface is captured using a matrix. And this geometry will then allow you to measure the instantaneous shape of the wavefront through a singular value decomposition process. And so singular value decomposition is used very often to solve the matrix which captures the geometry of connection between the wavefront sensors and the deformable mirror. It is not accounting for the missing adaptive optics. It is an integral part of adaptive optics most of the time. So let me stop there. I have answered most of the questions you have asked, and it was a pleasure talking to you, and hope you enjoyed the talks.